Not all mirrors are completely flat. In fact, most of the time we're actually dealing with a mirror with some slight curve to it. And so in this video, we're going to talk about those curved mirrors, also known as spherical mirrors. Now, a spherical mirror is shaped as if it's a section of a sphere. So let's say we have a perfect sphere. Well, what we're doing is we're just taking a chunk out of that sphere and shining light at it and looking at the reflection off of one side. In the example on the left, notice that the mirror is curved towards the light. So if we were to complete this as a circle, the center of curvature would be somewhere on the back side of the mirror. In this case, we would call it a convex mirror. Now, on the right, if we completed that curvature, made that a circle, we would see the center of curvature would be on the same side that the light is coming from. In this case, we're calling that a concave mirror. Now, here's how we're going to treat these concave and convex mirrors. We're going to first of all look at a concave mirror in just a second, and then we'll deal with a convex mirror a little bit later. But we are going to act as if these light rays are coming from faraway objects. And when they do, well, the light rays in this area coming into the mirror can be treated as if they are perfectly parallel. And it's not a bad approximation at all when you're dealing with objects that are far away. And so the light comes in and hits the spherical mirror, and following the law of reflection, the light is going to reflect and then move across the central line at some point. Now, all of these lines may or may not line up at the same point. When you have a mirror with a really large curvature, so you have a curvature of the mirror as being large in this case, then you're going to get kind of a mess. The points aren't all going to line up at the same point. However, if the curvature is small, meaning basically it would be a smaller sphere, if the curvature is small, then this light is all going to converge at one point. We're going to call that the focal point. So the focal point is the point where incoming light from a faraway object all converges at one point. That's the focal point. Now, if we use geometry, we can find the relationship between the focal length and the radius of curvature. Radius would be the distance from the center of this imaginary sphere to the mirror itself. Okay? So there is a relationship between the focal length and the center of curvature, and that is that the focal length is 1/2 of the length of the radius of curvature. So in this case, if I said that this was part of a mirror, a very large mirror that had a radius of 10 meters, then the focal point would be 5 meters. It would be 5 meters away from the mirror, this distance right here. That would be 5 meters where all of the light would converge at one point. Now, how do we avoid something like this? This is what we call spherical aberration. My term's right there. How do we avoid it? Well, sometimes we can avoid it by using what's called a parabolic reflector. It's not a perfect sphere, but it's a parabola. It's a parabolic sphere, a parabolic mirror. By doing that, it forces all of the light to be reflected at the same point. They can all cross at the focal point. However, doing that is much more difficult and expensive. So that's only used in particular circumstances, such as with telescopes and other research projects.